First chapter, as I said, it's about set theory. It's 4 parts. Part 1 is only about set and subsets. It's only basic things about sets. Here we have the definition of sets. We say, we say a set is a well-defined collection of distinct objects. This is the definition of a set. And the objects are called members or elements. For any set, we have some objects in it. And the objects are called members or elements. Here, we all defined, in the previous slide, we have well defined. Here it's explained what does it mean by well defined. We say, if a set is finite and not too large, we can describe it by listing the elements in it. As you see here, we have some examples. These sets are finite. As you see, we have a finite number of elements in it, in each of them. For example, A is the set of 1, 2, 3, 4, 5, 6, 7, 8, and 9. And also could be given as A is the set of all positive integers less than 10. So you should know what are the integer numbers. You say the integer numbers are 1, 2, 3, 4 up to infinity, then -1, -2, -3 up to -infinity, and also 0. These numbers are all together is called the integer numbers. Here it says A is the set of all positive integers less than 10. That means 10 is not included. It's only less than 10 and are positive. That is from 1, 2, 3 up to 9. That means A is the set of these elements. As you see here, these numbers which are in set A are called elements or members. Okay. B is a set of first 5 positive odd integers. First, we should write down the positive integers. The positive integers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. What are the first odd ones? The first 5 odd integers. This is an odd number. Odd man, I tagged it. Okay. This is the first odd integer, positive integer. And this is the second one. It's third, it's fourth, and it's the fifth one. And you are asked to write down these numbers in a set and name it by B. That means B is 1, 3, 5, 7, and 9. As it says, B is the set of first 5 positive integers. So we should first write down the integers and then pick all the 5 positive odd integers. And then we have another set, set C. It says is a set of vowels. The vowels, we have only 5 vowels in English language, which are A, E, I, O, U. We have these 5 vowels. Okay. These all sets are finite sets. Any of these is a finite set. Yes, for yourselves, you can read this. Okay, it's only about how to express a set. Here you have another example. It says listing all elements. A equals 1, 2, 3, and 4. We have some types of representation of sets. If the set is finite, it could be represented by all its elements. As you see here, A have only 4 elements. In A, we have only 4 elements, and it could be represented by all elements. As you see, A is 1, 2, 3, and 4. And also, it could be written by a pattern. The set of natural numbers, this n denotes the natural numbers, and the natural numbers is the set was starting from 1, 2, 3, 4 up to infinity. Only the positive ones. And the natural number is 1, 2, 3, 4, 5, 6 up to infinity. These numbers in a set is called the natural numbers. So the natural number could be expressed as a pattern 1, 2, 3. Then we just write down 3 dots. That means it's going, go. Okay. And also we can use the set built-in notation for expressing a set. We say P, the set of all x, such a way that x is in R and x doesn't in C. Here it says P is the set of all those numbers which are in R but not in C. What are R and C? We say R is the set of all real numbers. It includes all positive real numbers and negative real numbers, rational and irrational. All of those numbers together is called real numbers. C is the set of complex numbers. Here we have imaginary and real parts for the complex numbers. And these are only basic things, actually. Here we say if we have repeated elements in a set, or sorry, in ordering. Here, this example is about ordering the elements. Ordering the elements is not important. For example, this is set A. A is 1, 2, 3, and 4. It could be expressed as 2, 3, 4, 1, or 4, 1, 3, and 2. These all are equal. Okay, ordering the elements is not important. For example, if we take another example, let's say B to be 1, 3, 5, 7. It equals to 7, 3, 5, 1. And also equal to 3, 5, 7, 1. It also equal to 5, 1, 7, and 3. Any of these representation of that set is the same. All of these are the same. And the repeating elements is not allowed in expressing the set. For example, here, when you say A, B, C, A, C, as you see here, this set, we have repeating elements. C is repeated, and also A is repeated. It could be written as A, B, and C. We don't have to write down the repeating elements in a set. Okay? If you have any repeating of elements, we should remove it. And here also we have 1, 3, 3, 5, 1. We should write down the set with no repeating elements. As you see here, 3 is repeated, and also 1 is repeated. So you should write down as 1, 3, and 5. Okay? Repeating elements is not allowed in representing a set. And here we have these two symbols, this and that. This symbol stands for belongs to. If an element belongs to a set, we say the element, then this sign, and then the set. For example, if we have A to be 1, 2, 3. Here we say 1 belongs to A. 1 belongs to A. And this symbol is used for doesn't belong to a set or anything else. For example, here we say 4 doesn't belong to A. As you see, in set A, we have no 4. We have no 4. So it's how if we have an element in a set or not. And here we have examples about the previous slide about belonging or not belonging to a set. X is the set of A, B, C, D, and E. We say B belongs to X. B is in the set X, so we say B belongs to X. But M is not belong to X. Say M, as you see here, we cannot find M. That's why we say M doesn't belong to this set. And for this one, for this set, we say A is the set 1. This is set 1, not only 1. Okay? Set 2, 3, and 4. Here, 3 belongs to A. 4 belongs to A. And the set of 1 belongs to A. The set of 2 belongs to A. But here we cannot say 1 belongs to A. As you see, the set 1 is belongs to A, not 1 itself. Okay? As you see in the set we have set 1, set 2, 3, and 4. 3 and 4 are belong to the set A, but 1 and 2 are not. But their sets are. Here, 1 doesn't belong to A, but the set 1 belongs to A, and also 2 belongs to A, 3 and 4 also. And here, set 1 belongs to A, and 1 doesn't belong to A. One doesn't equal to set 1. These are not equal. But we can say 1 belongs to set 1. Yeah, it's true. Because here we have only one element in the set, which is 1. We can say that. And here also we have defining a set. Let S be a set. Then the notation it could be expressed as A is the set of X. X is the elements, represents the elements. X, where X belongs to S, and this is the condition on X, P of X. Here, generally written, but P of X means the condition on X. Or we can say it equals to X belongs to S, where we have this condition on X. As you see here, we have this example. We say, let A to be 1, 2, 3, 4, 5, and 6. We can also write A as this. A equals X, where X belongs to Z. Z is the set of integer numbers. And X is between 0 and 7. This is the condition on X. Okay? This is the condition on X. What are the integer numbers? The integer numbers, I'm going to write down here. -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, and so on. Okay? We say A is the set of all those elements which are in Z. But the element must be between 0 and 7. What are the elements from 0 to 7? 0 and 7 are not included because here we have no equality. We have no equality. That means 0 and 7 are not included. And the numbers between 0 and 7 are all included. from 1, it's 0, is not included, and 7 is not included also. These elements are the elements of set A. This is P of X that I talked about before. I said that's the condition on X. And here, say, let B be the set of those elements of Z where X to be bigger than 0. That means from 0 to infinity, but 0 is not included. If there is equality here, we say 0 is included also. But here, 0 is not included. That means the set of integer numbers which are bigger than 0. So we start from 1, 2, 3 up to infinity. That means B is 1, 2, 3, 4 up to infinity. These are the types of representing of a set. This is the notation, and that's elements. Now we have the defining of the sets. We have these noun sets. N means the set of natural numbers. As I said before, it starts from 1, 2, 3 up to infinity. That's 1, 2, 3, and then we just write down the pattern. And for Z, Z is the set of integer numbers. It's the set of integer numbers. It's all positive, negative, and 0 numbers. Okay? This is the set of integer numbers. Then Z positive means the positive integer numbers. What are the positive integer numbers? If you look the previous step here, the positive ones are from 1 to infinity. This is Z positive. And Z negative are the negative ones. So Z positive is the set of all positive integers. And you have the rational numbers. Rational numbers are the fractions. All the fractions are the rational numbers. I have 2/3, 5/7, and so on. Okay? Here, these all numbers are belong to the Q. And also, we can write down Q as the set. We say it equals A over B, where A and B are real numbers. A and B are real numbers, but the denominator must not be 0, because any division by 0 is undefined. The denominator must not be 0. We say any division by 0 is undefined. So this is the definition of rational numbers. And we have irrational numbers. Irrational numbers, if we have a number which couldn't be get out to the root, to a root, pi or exponential, these are irrationals. Okay, because we have infinite decimals without repeating. We have infinite decimals without repeating. And the set of real numbers is the union of these two sets. It's all the numbers. All of these set of numbers together is called the real numbers. So the real number is the union of rational numbers and irrational numbers. And we have these symbols. It's only the define of these symbols. You can read by yourselves, okay? Now we have those symbols that we have here. We are going to talk about some of these symbols one by one. Subsets. We have subset and also proper subsets. For subset, we say if all elements of a set belongs to another set. For example, if all elements of set A belongs to set B, we say A is a subset of B. A is a subset of B because all elements of A could be found in B. And also, if we have two sets which are equal, we say each of these is a subset for the other one. For example, if we have A to be equal to B, if A is equal to B, we say A is a subset of B. Why? Because we can find all elements of A in B. We can find all elements of A in B. And also, we can find all elements of B in A. That means B is also a subset of A. If we have two sets, each of these is a subset for the other one, we say those two sets are equal. And the empty set, which is denoted by phi. It's denoted by phi. It's a subset of all sets. We can have the empty sets in all the other sets. For example, phi, when I say phi, I mean empty sets, okay? Phi is a subset of B. If B be any set. Phi is a subset of A, if A be any sets. Okay, so we say phi, which is the empty set, is a subset of all the other sets. And here you have an example. We have set A. A is 1, 2, and 3. And we say each set is a subset of itself. Each set is a subset of itself. So what are the subsets of A? We say phi, which is the empty set, is always a member of all the other sets. That means phi is a subset of A. Can I say 1 is a subset of A? Yes, because you can find 1 in it. So 1 is a subset of A. How about 2? Yes. 2 is also a subset of A because we can find 2 in set A. And 3. 3 is also a subset of A because 3 is a member of A. How about 1 and 2? It's 2 elements. Can I find both of these 2 elements in A? Yes, we have these 2 elements in A. That's why we say 1 and 2 is a subset of A. How about 1 and 3? Yes, we can. We say 1 and 3 are both could be found in A. So you say 1 and 3 is a subset of A. How about 2 and 3? 2 and 3 is also. We can find 2 and also you can find 3 in set A. That's why we say 2 and 3 is a subset of A. How about 1, 2, and 3? Can I say this is a subset of A? Yes, we can, because we can find all elements of this set in A. So the list of all subsets of A is these sets. Okay. So here, these sets are the list of subsets of A. As you see, the set A itself is also a subset of it. And here we say that every set is a subset of itself. And we have proper subsets. Proper subset means it belongs to the set, but not equal to the set. As you see here, these all sets are proper subset of A, but this one is not. It's not a proper subset of A because it equals to A. Okay. This is not, I mean, 1, 2, and 3, the set is not a proper subset of set A because it equals to the set. We say a set is a proper subset of another set if it doesn't equal to it. Okay. For the proper subsets, we say A is a subset of B, but it doesn't equal to B. It doesn't equal to B. That means A is a proper subset of B. We just remove this one. Okay? It denotes by this. We say A is a proper subset of B. If we write down this, we say A is a subset of B. Okay? For the proper subset, we have no this equality. That's all about it. Here we have an example. The proper subsets of A are 1, 2, 3, as you see, and also 5 was the empty set. And 1 and 2, 1 and 3, 2 and 3. But the set of all elements of A, which is 1, 2, and 3, this is a subset of A, but not a proper subset of A. يعني proper subset نبي إكسان ببسيطة. أبي برشة بلي بلا إكسان. So here we say the list of all proper subsets of A are these. These are the list of all proper subsets of A. And here we have another example. It's about proper subset. We say B is the set of 1, 2, 3, 4, 5, and 6. And A is the set of 1, 2, and 3. Here we can say A is a proper subset of B because A belongs to B, but not equal to B. That's why we say A is a proper subset of B. And we also can say A is a subset of B. We can say that also. Every proper subset is a subset, but not conversely. We cannot say every subset is a proper subset because as you see here, this is a subset of A, but not a proper subset. But here we can say every proper subset is a subset. So these two are both true. So you say A is a proper subset of B because you can find all elements of A in B and doesn't equal to B. Now we have another example. We say A is A, B, C, D, E, F, G, and H. B is the set of B, D, E. C is the set of A, B, C, D, E. And D is the set of R, S, D. Which of these sets, I mean B, C, and D, is a proper subset of A? Let's check from the first one, from this one. Here, can you find B in A? Yes. Do you have B in A? So you can find this element in it. And we also have this element here, E also. That means we can find all elements of B in A. And B doesn't equal to A. That means we say B is a proper subset of A. We can also say that B is a subset of A. Okay. How about C? Can we find all elements of C in A? Yes, we can. That means C is also a proper subset of A. And we also can say that C is a subset of A. For the last one, D is R, S, D, and E. Can you find all elements of D in A? No, because here we have R and S. And in A, we have no those two elements. That means D is not a proper subset of A. And even it's not a subset of A. Because we cannot find all elements of D in A. That's why we say D is not a proper subset of A. Only two of them are proper subsets of A, which are B and C. Okay? Now you have empty sets. Empty set is denoted by phi or this empty set. We have two curly brackets with no elements. It could be represented by this or that. These two are the representations of empty sets. Look, this one denotes an empty set, but this one is not. As you see here, we have a member. We have a member in this one, which is phi. This doesn't represent the empty sets, but this one is. If you have two curly brackets with no elements, that means that's an empty set. But if you have any member in it, we say it's not an empty set. Because here we have an element, which is phi. We say empty set has no elements. Empty set is a subset of any set. There is exactly one empty set. We have only one empty set in each set. We have no more than one empty set because all empty sets are equal. Properties of empty sets. We say a union, an empty set, if we find the union of any set with the empty set is the set itself. This is the set itself. And if we find the intersection of an empty set with any set, we get the empty set itself. Because there is no common members between them. That's why we say their intersection is an empty set. And here we say A intersection A complement. This dash, this prime means complement. We will talk about complement later on. We say A intersection A complement is an empty set. Also, a union A complement is U. U denotes the universal sets, which is the all sets. We say U complement is an empty set, and also empty set complement is the universal sets. We will talk about complement and universal set later. Here you have an example. So now we have this example. We say the set of x, where x is a real number and x squared less than -3. Since we have x squared and we say all the squared numbers must be positive, we have no number that is squared and it equals to a negative number. In the real numbers, we say we have no number that its squared is a negative number. We have no number to satisfy this equality in the real numbers. That means we say this set is the set of empty sets. It's an empty set. That means we have no number in the real numbers which we square it and it is a negative number. As you see here, we say x squared is -3. If we take the square root for both sides, we say x is square root of -3. Square root of the negative numbers in the real numbers is not defined. It's not defined in the real numbers. That's why we say we have no number in the real numbers that we square it and it is -3. If we have no numbers, that means there is no number, which is empty sets. And also, we say the set of x, where x is positive integer and its cubed is less than 0. Its cubed is less than 0. We have no number in the integer numbers. In the positive integer numbers, if we cube it and less than 0, because the cube of all positive integers is positive. It's still positive. That's why we say we have no number to satisfy this inequality. So we say it is also an empty set. We say if we have no number in that set which is given to satisfy the condition, if you have no number to satisfy the condition, means it is an empty set. Now you have equal sets. We say two sets are equal if they have the same elements. The same elements. For example, if A to be 1, 2, and 3, and B is also 1, 2, and 3. A and B are equal because they have the same elements. You have the same elements in both sets. That's why we can say A is equal to B. Now you have an example. Set A is A, B, and C, and B is B, C, and A. As you see, both sets A and B have the same elements. A, we have A here, and we have A here also. B, B, C, C. And we have no extra elements in any of these two sets. They have the same elements. And you can say these two sets are equal. You see A is equal to B. C and D. C is the set of 2, 4, 6, and 8. 2, 4, 6, and 8. And D is the set of 2x, where x is a positive integer and 2x is less than 10. Let's write down the positive integers: 1, 2, 3, 4, 5, 6, 7, and so on. Okay, you see D is the set of 2 times x, where x is a positive integer. We are going to multiply each of these integer numbers by 2. We get 2, 4. If we multiply each of these elements by 2, we get 2, 4, 6, 8, 10, 12, 14, and so on. What's the set of these elements which are less than 10? We have only 2, 4, 6, and 8. 10 is equal to 10. We say only less than 10. That means 10 is not included. What are the elements here which are less than 10? We have only these 4 elements: 2, 4, 6, and 10. That means D is 2, 4, 6, and 10. As you see, C and D are equal because they have the same element. Sorry, it's 8. 2, 4, 6, and 8. It's not 10. Thanks. Okay. As you see, C and D are equal because they have the same elements in. So you say C and D are equal. Equivalent sets. We say two sets are equivalent if they have the same number of elements. Okay, the equality of elements is not required here. Only the number of elements is required. For example, here A is A, B, C, D, E, and B is 1, 2, 3, 4, and 5. In set A, we have 5 elements, and in set B, also we have 5 elements. That means A and B are equivalent. We say two sets are equivalent if they have the same number of elements in. Here we say A and B are equivalent. Generally, we have two types of sets: finite set and infinite sets. Finite set and infinite set. Finite set is the set that you have a certain number of elements in the set. Here we say A equals 1, 2, 3, up to n. N is an integer. Okay, let's say n is 100, is 1,000. Okay, that means it has n points. N point. This set is a finite set. This set is a finite set, and in the set we have n elements. 1, 2, 3, up to n. If n to be 100, that means we have 100 elements in the set. So we have a certain number of elements in the set. So you say the set is a finite set. And here we have, let A and B be sets. A is 1, 2, 3, and 4. It's a finite set. We have only 4 elements in the set. B is the set of X, where X is an integer, and X is between 1 and 4. 1 and 4. 1 and 4 are both included also. If you write down the integers, 1, 2, 3, 4, 5, 6, and so on. And in this side also, -1. And so on. We say B is the set of integers which is greater than or equal to 1 and less than or equal to 4. That means 1 and 4 are included. We have these 4 elements in the set B. So you say it equals 1, 2, 3, and 4. If you have not these equalities, if you have not these two, that means it's only 2 and 3. Okay, since we have equality here, that means 1 is included, and also 4 is included. These two sets, A and B, are both finite sets. These two are finite sets. For the infinite set, we say if we have infinite number of elements in a set, the set is an infinite. The set is infinite, and also infinite set is uncountable. Is uncountable. Here we have these sets. We say C is 5, 6, 7, 8, 9, and 10. We have only these elements in the set. We have 6 elements in the set, so it's finite. For this one, we say X, B is X, where X is an integer, and it's between 10 and 20. That means 10 and 20 are not included. So set B is 11, 12, 13, 14, up to 19. Okay, it equals 11, 12, 13, 14, 15, 16, 17, 18, 19. This is set B. Here we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 elements in it. We have 9 elements in the set B. We say B is also finite. And D is the set of X, where X is an integer, and X is greater than 0. Greater than 0 means 1, 2, 3, 4, 5, up to infinity. That means here we have no finite number of elements in D. It equals 1, 2, 3, 4, and go and go and go. This set is infinite. It's infinite because we don't know how many elements are there in this set. It goes to infinity, so it's infinite. Set D is infinite set. Z. Set Z is the set of X, where X is an integer. X is an integer. That means it's the set of all integer numbers. It's the set of all integer numbers. Integer numbers is starting from -infinity up to infinity. Okay? So this set is infinite. We don't know how many elements are there in the set. It's infinite. And for the set S, we say it equals to x, where x is a real number, and x is greater than or equal to 1 and less than or equal to 4. Since here we talk about real numbers, we say between any two numbers, we have infinite real numbers. Between any two real numbers, we have infinite real numbers. That means it's infinite, because between 1 and 4, we have infinite numbers. We have infinite real numbers. It's defined in the real numbers. But the previous ones, it was in integer numbers. So it's infinite also. If this is integer, it would be finite. Okay? Between two integer numbers, we have finite integer numbers. But between two real numbers, we have infinite real numbers. That's why we say this set is infinite. And it's written here, C and B are finite, and the others, D, Z, and S are infinite sets. Now we have universal sets. Universal set is the whole set. If you have given a universal set, all the other sets which given must be subsets of the universal set. U is called universal set. We say all the sets, let's say you have set A, it must be a part of the universal set. That means A is a subset of the universal set. All the other sets must be subsets of the universal set. Look at this example. Here we have given sets A, B, and C. A, B, and C are given. These are three sets. If we choose the universal set for these three sets, we must choose a set such that all of these three sets are subsets of the universal set. Here we choose U to be 1, 2, 3, 4, 5, 6, 7, and 8. This is a universal set for these three sets. As you see, A is 1, 2, and 3. It's a subset of U. B is also a subset of U. C is also a subset of U. Here, the universal set for these three sets is this set. And any other superset of U will be a universal set. May someone else choose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. May someone else choose this one as the universal set. If you could find all the other sets, I mean A, B, and C in the set U, so U is the universal set. This is a superset of U. May someone else choose another set, okay? You could choose a set which contains all the given sets as the universal sets. And you have cardinality. Cardinality means the number of elements of a set. Number of elements. Okay? Cardinality means the number of elements. And the number of elements of a set must not be negative. must not be negative. It could be 0 because the empty set, the number of elements in the set is 0 and could be positive. As you see here, we say A is the set of 1, 2, and 3. How many members or elements do we have in set A? 3. So you say the cardinality of A is 3. Means we have only 3 elements in the set A. For B, we have 1, 2, 3, 4, 5, 6, 7. We have 7 elements in B. So the cardinality of B is 7. We have 7 numbers in the set B. So this symbol is used for cardinality for the sets, which is the number of elements of the set. And we have power sets. We have power set. Power of a set is the set of all subsets of the given set. For example, if A to be 1, 2, 3. So power of A is also a set. What do you have in power of set A? We have all the subsets of A. All the subsets of A. We say phi, which is an empty set, is a subset of A. As we talked about before, we said empty set is always a subset of all the other sets. 1 is a subset of A. B, 2 is a subset of A. 3 is a subset of A. 1, 2 is a subset of A. 1, 3 is also a subset of A. 2, 3. Then 1, 2, 3, which is A itself. This is the power of set A. We take all the subsets of the given set, which is the power of the set. And for making sure that you do or you find the power of the set correctly, look at the number of elements in the given set. We have 3 elements. We have 3 elements. So we must have 2 to the power 3 elements in the power of the set. The cardinality of the set is n. Then the number of elements in the power of the set must be 2 to the power n. Here it's 3. So 2 to the power 3 is 8. It's 2 times 2 times 2 is 8. Let's check if we have 8 elements in power of A or not. It's 1, 2, 3, 4, 5, 6, 7, 8. So that's correct. You must have 2 to the power n elements in the power of the sets. As you see here, we have given the same examples I talked about. Power of A is this set, which we have 8 elements in the set. And the cardinality of the power of the set is 2 to the power n. N is the cardinality of the set. Also, as the summary, we talked about the sets, and we said ordering is not important in representing a set. So we must have no repeated elements in the set. Yeah. As I said, if we have repeating elements, we must remove the repeating ones. And we also talked about if an element to belong to a set or not. And as you see here, X belongs to A. Yes, if yes, that means X must must be in A. If no, X must not in A. But all the elements are in the universal sets. Must all elements are in the universal set. And here you have 3 exercises that you should do by yourselves, okay? So if you have no questions about the first part of chapter 1, I'm going to talk about part 2. It's also about set theory. It's all about the same topic. It's the same as the previous part. We have union. We have operations on sets. We have union, intersection, difference, complement, and so on. Other operations on sets. First, you have union. For the union of 2 or more sets, we are going to write down all the elements of the given sets without repeating. Okay? Here, we say A union B is the set of all elements of A or B. Okay? And using Venn diagram to represent the union, we say if this is set A and this set B, so the union of them is the green one, green area. The green area is the union of sets A and B. And also, the cardinality of A union B, the cardinality of A union B is the cardinality of A plus cardinality of B minus the cardinality of A intersection B, if they intersect their common elements. Here you have an example. We have given A, B, and C, and we should find A union B, A union C, B union C, and also A union B union C. What we do for the first one, A union B. Sorry. We don't talk about cardinality here. If you see these 2 lines, then it's about cardinality. But here you have not these 2. It's only finding A union B. We just find a set. Okay? As you see before, if you see this form, then it's about cardinality. Here, for A union B, we say we are going to write down all the elements of A and B without repeating. The easiest way for doing that is writing down the elements of A first. 1, 2, 3, 4, and 5. And then write down the elements of B. Which ones? Only those which are not in A. Only those which are not in A. If you write down B, B is 2, 4, and 6. As you see here, we have repeating elements. But we said we must have no repeating elements in the sets. So 2 is repeated. So we just remove it, and 4 also. 2 and 4 are repeated. So you just write down 6. This is A union B. For A union C, we are going to write down set A first. 1, 2, 3, 4, and 5. Then C, 8 and 9. We are going to write down both because we have no those 2 elements in A. B union C. B is, we first write down elements of B, which are 2, 4, and 6. Elements of C are 8 and 9. None of them are in B. So we write down both, 8 and 9. For the last one, A union B union C. Write down the elements of all sets without repeating. A is 1, 2, 3, 4, and 5. Then B. What are the elements of B which are not in A? Only 6. Is it? And elements of C. What are the elements of C which are not listed here? 8 and 9. This is A union B union C. So how about A union B? It's cardinal. It's cardinality. We say it equals the cardinality of A plus cardinality of B minus cardinality of A intersection B. First, we should find, sorry, it's the same. A union B and B union A are the same. Yeah, it's commutative. We will talk about that. It's commutative intersection and also union are commutative. We say A union B is the same as B union A. Okay. And for this one, for the cardinality of A union B, we say it equals. What's the cardinality of A? How many elements do we have in A? 5. Plus cardinality of B, 3 minus A intersection B. What are the common elements of A and B? 2 and 4. So A intersection B is only 2 and 4. What's the cardinality for this set? It's 2. Is it? We have only 2 elements in A intersection B. Minus 2. So it equals 5 plus 3 is 8. Minus 2 is 6. Look, we have only 6 elements in a union. And for others, the same. And you have intersection. For the intersection of 2 sets or more, we just write down the common elements. We just write down the common elements of the given sets. Here we say, I'm just going to talk about intersection and synapticity. A Venn diagram for A intersection B is the common part. As you see here is the green one. Only this part is the intersection of A and B. Only the common elements. We have this example. We have given W, X, and Y. And you should find W intersection X. W intersection X. We should pick only the common elements of W and X. This is W. Do you have 1 here? No. So you don't write down 1 here. How about 2? Do you have 2 in X? Yes. So you write down it. 3. Do you have 3 in X? No. Do you have 4 in X? Yeah. In X, yeah. You have 4 in X also. 5. Do you have 5 here? No. 6. You have 6 here. So this is W intersection X. Just compare the sets element by element. If you find any element which in both sets, it's in the intersection. For W intersection Y, W and Y, these 2 sets. 1. Do we have 1 in Y? Yes. 2. We have 2. 3, 4, 5, and 6. We have no those elements here. That means this is W intersection Y. For Y intersection X, Y intersection X and X intersection Y are the same. We are going to find the intersection of these 2 sets, Y and X. 2. You have 2 here. Do you have it here? Yes. Four. We have 4 here and we have no 4 in Y. 6. We have not in Y. 8. We have it in Y. 10. Yes. This is Y intersection X. And for the last one, we must find the common ones which in all sets in X, Y, and W also. We are gonna do one by one. Look, 1. we have no one here, so we just ignore it. Okay. 2, we have 2 here, and we have it here. We have it here also. So 2 is a common element in those 3 sets. 3, we have 3 here, but we have not here. We don't care about the other. We just ignore it. 4, we have 4 here. You have it here, and you have not here. So you don't write down 4 also, because it's only in 2 of the sets. It's not in all the sets. 5, we have no 5 in the other sets. 6, we have 6 here, we have not here. So that's all. We have only 2 as the intersection of wx and y. So the intersection of wx and y is only 2. Okay, and it's enough for today. If you have any question, you can ask.